Facebook for our internal use cases.
Let's all thank Kinjal again in chat. We're going to move on to our next talk, which is Avi Bryant, who's running Gradient Retreat. Sorry, Avi, I don't know why I pronounce your name as Avi. It's Avi, presumably. We're ready when you are.
Okay. I think you can all see my screen now. I'm going to talk about some work that I did mostly last year on a new computation graph meant to support PPL, but I'm going to talk more about the computation graph than about the PPL. The PPL is Rainier. You can look at the website at rainier.fit. And kind of down below there are the important things to know about it. So it's supporting, kind of finite fixed structure models with continuous parameters. So similar to Stan. And it's using Hamiltonian Monte Carlo to do sampling. And the thing that distinguishes it mostly is that it is running fast on in a pure JVM environment by doing dynamic compilation to JVM bytecode. And it's actually that kind of engineering compilation aspect that I'm going to talk about today. So the context here was for production use at Stripe. And that's where I was working when I started this work. And Stripe is a payment processor. The context, more or less, was that we wanted to be able to model, so Stripe's customers are merchants, they're people selling things online, and we wanted to be able to model the risk to Stripe of effectively extending credit to these merchants. And so we're trying to weigh the probabilities of long tail events like merchant bankruptcies or like merchants turning out to be fraudulent against the kind of more common cases of typical operations and what the cost to Stripe of those different cases would be. But the work was driven more by what I would call the operational context of working in production at Stripe. And what I mean by that is that we wanted to be able to run a very large number of models in production on kind of a daily cadence on what Stripe had in terms of infrastructure, which is a large cluster of JVM workers. And in Stripe's production context, it was important that we be able to run on the JVM and that we be able to run on the JVM without, linking in other libraries or spinning off other processes, just kind of as vanilla as possible. And really what this is about controlling novelty or making trade-offs on novelty. And what I mean by that is that because what I was proposing, what my team was proposing, was in Stripe's context, a novel way of doing modeling. That is to say, Stripe did not have other PPLs in production, did not have other Bayesian models in production. And so this was considered a risky thing to be doing from that perspective. It was important that we keep the operational novelty very low. That is, if we were to propose something that was both novel from a modeling perspective and also novel from an operational perspective, that would be unlikely to succeed or even be allowed to happen. And so by keeping the operational novelty very low, we were able to take more risks on the modeling side. And so what the goals ended up being, we were targeting Stan-like models running with HMC for sampling, but we wanted to be able to run on vanilla JVM, on vanilla hardware, so notably no GPU, and still have performance be as fast as possible. And the approach we took was to build a library in Scala, because that's the language that we were most comfortable with, that builds a static compute graph very similar to TensorFlow in its static mode. Use autodiff, again, a fairly vanilla autodiff. But then these two kind of more novel things that I'm going to talk about in this talk. One is this incremental partial evaluation while building up the compute graph to do quite a lot of optimization. And then the other is once we have the optimized compute graph to dynamically compile it to as low level as we can, JVM bytecode, so that the inner loops of the samplers are running very fast. So I'm going to talk about how we kind of went about that. So let me explain what I mean by partial evaluation. And so anytime you have a library for doing this kind of modeling, you are going to be building up your model of a bunch of existing functions or methods that are defining things like common distributions and so on, right? And so you might well have in that library an implementation of the log PDF of a Poisson distribution, for example, given a particular lambda and particular observation, right? And so that would look something like that line at the top. But in its use in your program, you are going to be composing this with other functions. And so, for example, what you pass in for the lambda might well, from some, have a link function like an exponential link function. And so what you're passing in might be e to the x, where your actual parameter is x. And so, typically, because you're just reusing these pre-written library functions, that would be doing something somewhat inefficient in that we're, taking e to the x and then immediately taking the log of it in this kind of generic Poisson log PDF function. And what we want to be able to do is do this kind of whole program optimization where we see that no matter what the value of x is, we can always just take y times x rather than y times log of e to the x, right? And we want to do that partial evaluation once, and then use that optimized program in every time we do the sampling, right? What gets even potentially more valuable, or is valuable in combination with this kind of whole program optimization, is to do a partial evaluation or a specialization of the function to the observations, to your data. Because again, that is not changing on every iteration through your sampler. You've always got the same observations. You're just changing your theta, you're changing your parameters. And so if you can do some amount of the computation of the parts of your program that only depend on your data ahead of time, then you can potentially save a huge amount of work. And so this is a bit of a worked example for Poisson, where we can make the observation that if our observation y is not a single scalar, but is a vector, what we are going to end up wanting to do for, say, our likelihood of this model is summing the individual Poisson log PDFs of those scalars to get the overall log PDF of the vector. And that we can look inside the function and see that, in fact, the sum of this function over the entire vector, we have these two terms in it: the log lambda times the sum of the values, and then also the sum of the logs of the factorials of the values that depend only upon our observation data and not at all upon our parameters. And so we can pre-compute those terms and then treat those just as constants. And when we're actually doing the sampling, we have saved a lot of work. And in fact, we have changed the asymptotic complexity of evaluating this density function from being order n in the size of the data to being order 1. And so that can be a huge performance optimization. And again, this might take some time, but we're doing that once for the model, given the input of a certain piece of data, and then we're going to evaluate the density function or its gradient millions of times, and so that's valuable. This is a slightly longer worked example that shows that in some cases you might need to do some kinds of transformations, like in this case expanding out this exponentiation of this term to get to a form that has terms that kind of do reduce to these constants, but for example in a normal PDF, normal likelihood, that also, this same kind of optimization applies. And it applies surprisingly often, even when you are composing, a much more complicated model than just a single simple likelihood function. So I'm going to talk a little bit about how that works from an implementation point of view. And one thing that's unusual about our approach to this is that it happens incrementally as the program is running, building up the model. And so what I mean by that is that in the Scala program, you have values that represent these compute graphs. And so, for example, you might start with a value that is just the parameter x. As in, again, TensorFlow or NumPy or, any number of things, if you send the log method to that value, then you get back a new graph that represents the log of x, and that's, quite straightforward. And what I mean by incremental partial evaluation is that if you then call the x method on this new value, you do not get a new x node, but it recognizes instead that what we have here is simply x, and that will be the value that is returned. And so in the construction, during the construction of these DAGs, it is performing this kind of incremental evaluation. That's not a very interesting example. Here's a slightly more interesting example. And what I'm going to show you first is kind of the naive or kind of typical way that this DAG would be constructed. So if we had x and y parameter nodes, and we evaluated x plus y, then we would expect to return a graph that had this binary operator node that references the two values. If we add in another x, now we get to see that it's a DAG, not a tree, and we can see that this new binary operator plus node references the earlier graph, and again references for a second time the x value. And similarly, if we then multiply by 3 and so on, and the graph just keeps growing, right? We chose a different representation for arithmetic operations that would keep graphs more compact and allow more of this kind of partial evaluation to happen. And so the representation that we chose is that addition is represented by a vector that is basically the coefficients or the other side of a dot product with the child nodes. And so what I mean by this is that this node represents 1 times x plus 1 times y. And so obviously that is just x plus y. But what that means is that now if we move on to adding another x, then we can recognize that all that we need to do is just increment the coefficient or change the coefficient on the x. And so this node now represents 2x plus y. And similarly, if we multiply by a scalar, all that we need to do is distribute that multiplication into the coefficients. And so this node now represents 6x plus 3y. And so we can say that these nodes are, they're closed under addition, right? So if we have one of these nodes, which we call a line node, and we add it to another line node, we can simply merge the coefficients, and we get back another line node. And the size of our graph hasn't changed at all. And similarly, if we multiply by a scalar, which is a fairly common operation, we get back another line node, and the size of our graph hasn't changed at all. It's worth noting that if we add in a third term or a fourth and so on, that the size of the vector just expands. But again, the number of nodes in the graph has not changed. We take this up kind of to another ring, to the multiplication and exponentiation ring, which is to say that if we multiply by some non-scalar value, then we end up with a very similar node structure, but where this represents the product of the terms raised to a certain power, right? And so this is z to the 1 times, that whole other term of 6x plus 3y to the 1. And if we multiplied in another z, we'd get z squared. And if we exponentiated by a scalar and so on, we'd be able to handle that in the same way. And so these nodes are closed under multiplication and closed under exponentiation by a scalar. So that novel representation of the nodes as we're building up the compute graph actually leads to, in practice, what we have observed, very compact graphs and a great deal of opportunity for this kind of partial evaluation, just in that choice of representation. I'm going to talk a little bit then about the compilation side, right? Because once we have this DAG, then what we want to do is we want to compile it to JVM bytecode, and we want it to run as fast as possible. And so, and we want it to be, a simple compiler that we can work with. And so, what we compile to is a target that is an extreme subset of the JVM. So it's a subset of the JVM with absolutely no allocation. And on the heap, obviously, stack frames still get allocated potentially. The reason that we want that is that the biggest impediment or kind of variable in the performance on the JVM is garbage collection. And so if we can avoid ever allocating any objects, then we can guarantee that the garbage collector will never need to run during sampling, and that helps immensely with performance. We also have this weird kind of constraint that when we are compiling, sort of naively, what we would want is we would want to take our compute graph and we would want to just compile that down into a single gigantic method on the JVM, right? And that would be convenient in part because then we can use temporary variables, local variables for everything, and we don't have to worry about kind of control flow passing back and forth between functions and so on. Unfortunately, in its default settings, the JVM has this restriction, which is that it will not compile to machine code with its just-in-time compiler any method that is larger than 8,000 bytecodes. And so we need to split our methods up so that the individual methods stay small. And that in turn means that to avoid doing work over again, we need a way to store temporary values. And so what we chose was to break it into small methods, each of which take 2 arrays of doubles, pre-allocated arrays of doubles as parameters, one of which is all the inputs, basically constant values that we need to evaluate our model, including parameter values. And the second is basically a scratch buffer. We sort of treat it like a pre-allocated heap of memory that we can write temporary values into.
Hi, Avi. Sorry for the late reminder. You're slightly under 5 minutes.
Okay, thank you. And the return value of these methods is always a single double because we're always just interested in computing a log p. Just quickly, results. So we benchmark using some of Stan's benchmark models. In some cases, as you can see, we were much faster than Stan. This is only looking at gradient evaluation, right? I mean, the Stan sampler is much more sophisticated than our HMC sampler, but just looking at gradient evaluation time, in some cases, we were much faster, 20 times faster than Stan. In some cases, we were twice as fast. In some cases, we were half as fast. It's interesting to look at the kid IQ regression example in particular that shows that asymptotic complexity. And so, we are faster 10 microseconds versus about 40 microseconds when using 100 data points. We are faster, again, just 10 microseconds using 200 data points. And you can see that the Rainier evaluation time does not change as you increase the data points because it was able to pre-compute everything about the data, and always the only thing that matters is the parameters changing there. So I'm going to stop there. You can look at rainier.fit. You can get in touch with me, and I'd be happy to take some questions.
All right, let's all thank Avi for a great talk. We have a couple of questions which I think we could do briefly. One question from Chad Scherer is he would love to hear about your representations of summations, and he's noting maybe it was going to come up in the talk, but I don't think I did.
So I think, depending on when you wrote that, Chad, so I did talk about the representation of kind of individual additions. And then I think the other thing to say that I didn't have time to get into is that there is effectively an implicit summation on the compute graph over the data set. So that's to say that we know that the structure of these of these log p functions is that we are going to compute the log p. We're going to have a prior that we evaluate once, depending on the parameters, and then we are going to have likelihoods that we compute once for each value in the data that are going to have the same structure, and we have this kind of implicit summation over them. And we have multiple likelihood functions and multiple data batches and so on that go into the same model, but that is kind of where the implicit summation is. And so actually anywhere that there is a constant in our compute graph, that constant can be a vector, but that vector is always assumed to have this kind of implicit summation of the entire subgraph of the compute. So hopefully that made a little bit of sense. I didn't really have time to get into it.
Great. And so I have a second question from Adam Pocock, which I think is at least tangentially related. It's a fairly technical question, which is that if you build things without loops, then the hotspot C2 compiler probably can't auto-vectorize. Did you see if the compiler managed to auto-vectorize any of your operations?
So that's correct. So that's one limitation right now, is that there is no use of SIMD instructions that gets emitted by the JIT compiler. It's really very difficult to guarantee that it's going to use those. We definitely, that's kind of a future work thing, is seeing if we can do that. The more immediate future work is to make the computation data parallel, which is much easier, and I have done some experiments with already. So we can't do SIMD, but we can do multi-core, and not multi-core with multiple chains, but like even within a single gradient evaluation, do multi-core just across the data. Again, basically because we're very aware of that implicit summation across each of the log P's for the individual data items.
Great. Avi, thank you again for your talk.